Hello, my name is Kofi Makinwa. I'm a professor at Delft University of Technology, and today I'm going to at least attempt to demystify auto-zeroing. You've probably heard a lot of things about auto-zeroing because it's a widely used technique. You've heard some good things, that it reduces offset, low frequency noise and drift, but you probably have heard some bad things about it as well. That is that it increases your low frequency noise floor and requires huge caps. So the object of this talk is to introduce you to the basics of auto-zeroing so that you can make up your own mind. So here's the basic idea. This is a block diagram of an auto-zeroed system. Fundamentally, it works in two phases. So what you're seeing over here is the auto-zero phase. During the auto-zero phase, the offset is sampled by a sample and hold and subtracted from the original offset, resulting in an output voltage of 0. During the subsequent amplification phase, the signal is present and also the offset of your system. But because your sample and hold remembers the stored value of the offset, the final output just contains the input signal. So the offset has been cancelled. Now, what insights can we gain from this simple block diagram? Well, we can see firstly, that this is a two-step process. And if you do this on an amplifier, it means that the amplifier is going to be periodically out of office, right? So during the auto-zero phase, you can't use the amplifier to amplify the input signal. Also, what you can see is that the offset is being sampled. And that means that any noise associated with the offset will be sampled as well, which means that you always run the risk or will always suffer from noise aliasing. Last but not least, you can imagine that if this auto-zeroing process happens periodically, that it will act to cancel drift and one-over-F noise, provided the sampling frequency is high enough. Here's a circuit implementation. So here's one way that you might implement auto-zeroing. So here I have a real amplifier, which I've modeled as the combination of an ideal amplifier and an offset source, and I'm going to auto-zero it. So in the auto-zero phase, these switches, S1 and S2, what they do, switch S1 short circuits the input. So now the amplifier only sees the offset voltage, and switch S2 configures the amplifier as a unity gain buffer. What does this mean? This means that the offset gets stored on the auto-zero capacitor. Now during the amplification phase, we open switches S1 and S2, and the result is that the stored offset voltage on C auto-zero actually cancels the amplifier's own offset, and so the amplified voltage at the output of the amplifier is proportional to the input signal multiplied by the amplifier's gain. So basically we have cancelled the amplifier's offset. But yeah, nothing is so simple. So now we have to talk about the fine print. First of all, there are a number of sources of residual offset. So you want to cancel offset, but there'll be some remainder. And in this particular implementation, one source of residual offset could be the fact that a practical amplifier will not have infinite gain. A practical amplifier would have a finite DC gain, and as a result, its gain during the auto-zero phase is not exactly 1, it's a bit less. And the net result of this will be a residual offset, which is proportional to the original offset divided by essentially the gain of the amplifier. Now, since the gain of an amplifier can be pretty large, in the order of, let's say, 10 to the power 5 or even 10 to the power 6, this may not look like a significant drawback. But if you start out with an offset of a few millivolts, you can easily reduce it to the microvolt range. Another more important source of residual offset occurs due to the charge injection of this switch S2. When this switch opens, it will inject charge into the auto-zeroing capacitor. And this will cause a residual offset that is given by the amount of injected charge divided by the capacitance value. And just to give an example, in a 0.7 micrometer process, if you would use a 10 picofarad cap with a minimum size sampling switch, NMOS, that will give you a charge injection of about 250 microvolts with, assuming that you have a 2.5 volt logic transition change in the overdrive of the MOSFET. 250 microvolts is quite a lot, especially when you're trying to achieve microvolt levels of offset. So what can we do about this? Well, the first line of defense is to use differential topologies. Why? Because then you can be reasonably sure that the charge injection in both branches of the differential circuit is more or less the same, and therefore you will get first order cancellation of charge injection due to the common mode rejection of the amplifier. Another thing that we should do is to remember that charge injection is proportional to switch area, so we should always try and use minimum size devices. Of course, we also have to be worried about thermal noise, so this and settling time, so this may not always be possible, but this should be the direction in which we're trying to design. Another obvious step is to make the auto-zeroing cap as large as possible, and even better, place it after some voltage gain. So do the auto-zeroing after the offset has been amplified by a certain factor. And then last but not least, we can get local cancellation of the switches charge injection by using transmission gates and or dummy switches. But I must stress these will only result in partial cancellation of charge injection because of the inevitable mismatch between, let's say, a PMOS device and an NMOS device, and a dummy switch which of necessity has to be smaller than the main switch. So that was about offset. What about noise? Well, the key element of an auto-zeroed amplifier is a sample and hold. And here's an old schematic which you may remember from your early signal processing classes. This is a sample and hold circuit. And its switch will always have a certain resistance associated with it. This resistance generates thermal noise, and when this switch opens, the sampling switch, this thermal noise, the instantaneous value of this thermal noise, will be sampled on this cap. Now, from your old signal processing classes, you should remember that the amplitude of the noise on this cap, this is an RC circuit, will be kT over C, the square root of that. And if you have a 10 picofarad cap at room temperature, that the worst case amplitude that you could get sampled on this cap is in the order of 20 microvolts. So that's also quite significant. It gets worse, because actually this 20 microvolt level noise is held during the amplification phase. And that means that actually the process of sampling and holding noise actually exacerbates the noise energy. Now, the mathematics behind this is all very complicated, so I've chosen to show this with a simple simulation. So here's a simulation of a very straightforward sample and hold made by an NMOS and a 10 picofarad capacitance. On the right, what you see is the noise spectrum. Here's the amplitude in volts per square root hertz, and here's the frequency. And you can see two plots. One is the plot of the noise spectrum of this RC network when the switch M1 is always on. So then you just have a straightforward RC network, and you can see the white noise which be filtered and finally will roll off for the first order response. This is the noise spectrum that results when you turn on the sample and hold. Because of this process of periodically sampling the noise and holding it, the noise at low frequencies explodes dramatically. And in fact, in this case, it's about 6 times. And this just happens due to the fact that you're sampling and holding the noise at a frequency of about 100 kilohertz, which is lower than the bandwidth of the noise, and therefore you're getting some noise aliasing. Now, okay, so that was the sample and hold. The sample and hold is only one part of the auto-zeroing amplifier. So let's look at how the sample and hold noise affects the whole system. So here's a block diagram of the sample and the auto-zeroing system again. But now instead of offset, I'm just showing you the input noise. And the output noise is the result of sampling this input noise and subtracting it from that noise, getting a smaller noise signal. At least that's what you hope. Mathematically, you can express the output noise as being the input noise multiplied by a transfer function, which is 1 minus h of f. H of f is the frequency response of the sample and hold filter. What is this h of f? Well, that's not too mysterious. We know this to be a sinc function. So, and a sinc function is a low-pass filter. So actually, 1 minus h of f is a high-pass filter. And that actually explains how auto-zeroing actually works in the frequency domain. It's a high-pass filter, and therefore auto-zeroing naturally rejects offset. And because it's a filter, it will also reject low-frequency noise. But because this is a sample and hold, and we are sampling the signal, and the noise bandwidth will typically be much wider than our sampling frequency, we will suffer from noise aliasing. When you put all these things together, you come to the final output spectrum of an auto-zeroed amplifier. So in bold on this plot, where I'm showing the noise amplitude again versus frequency, you see the spectrum before auto-zeroing. You may recognize 1 over f noise and the 1 over f corner and then a flat thermal noise floor. And after you apply auto-zeroing, what you will see is that the 1 over f noise has been reduced or cancelled if the sampling frequency is high enough. The 1 over f noise will have been cancelled, but you will still have a higher residual noise floor at low frequencies. And this is very characteristic of the behavior of an auto-zeroed amplifier. And if you are the mathematical type, I recommend you to have a look at the classic paper of Enz and Temesh, which gives you all the mathematical gory details. So to summarize, what have I explained about auto-zeroing? Well, auto-zeroing works. You can get low offset because it behaves like a high-pass filter, and we can get offsets in the range of 1 to 10 microvolts. It's a fundamentally discrete time process. It takes 2 steps. And that means that if you want to achieve continuous time operation, you have to do some extra things. I don't have the time to describe them in this talk, but I give you some references. You can make so-called ping-pong amplifiers, basically 2 auto-zero amplifiers operating in antiphase. And there's a good paper by Petais about that. Or you can use offset stabilization, where you use actually an auto-zeroed amplifier to stabilize the offset of a main amplifier that is continuously operating. And this is another good paper. Another issue of auto-zeroing is that because you are sampling, you will get noise aliasing, and this will increase your low frequency noise. 2 tricks: you can shift it away from DC by chopping the auto-zeroed amplifier, and here's a reference for that. Or if you take steps to dramatically reduce the noise bandwidth, you can reduce the excess noise at low frequencies down to square root 2 of the original noise. And square root 2 is about 1.4, so you're actually getting pretty close to a flat noise floor. Last but not least, I should stress that despite, let's say, some of these issues, auto-zeroing is the technique, the low offset technique of choice in discrete time systems where you are basically sampling anyway. So because you're sampling anyway, these issues of noise aliasing and so on already exist in your system. And therefore, you can add on auto-zeroing without any further penalty. And therefore, auto-zeroing is well suited for use in switch capacitor filters, image sensors, Nyquist ADCs, and the like. So, thank you for listening. That was it for now.